Thanksgiving is so good.
Most of my friends I have
No, Thanksgiving. What is it? Is it the third Thanksgiving?
Thank you for keeping up the concept. I don't know if you're not doing it voluntarily or involuntarily, but I'm pleased to see someone. You know, there is a cartoon calendars, this for each day, little story. So one of these cartoons was like instructor coming, speaking the audience in the class. Next time, instructor is coming, no one in the class, only the tape recorders. And the third one, there is no instructor, there is a tape recorder on play, and the tape recorders will record. So, if you do have complete understanding of the both sides of this little printout, then you can either leave or win back and relax. So we do have 6 meetings in class if you do presentations on that week Friday, and 6+1 if you decide on the 19th. The plan is to absolutely accomplish all calculations on coming Wednesday, and one more Wednesday will be just to prepare videos for your presentations. The written reports are suggested to be in final form next Monday. Okay? So whatever you collect data during the Wednesday, on Friday there will be no lecture in regular sense. Instead of the class material, I will entertain you with my humble vision how to write papers. It will be silly, you know, I will give you some suggestions how to organize and put it short and then on Monday you bring your written reports printed, 3 or maybe 4 copies. 3 for sure. You have an idea of that. Okay? So that will make my life easier. And then on the coming Monday, after you do collective grading, your authors will get their works back and do last evaluation. But since it will be a busy week, it's better to have as good as complete final version than Monday. Do you think it is doable?
So is that report on our project? Or
Yes,
is it on
report on the project. And do not worry, all projects, like they have good scientific component, they are not challenged. But each project, and we are spending like a month on that, but each project is possible to accomplish in 1 hour. And write down in 2 hours. We're just doing it a little slower so that we have time to think and make strategic plans. So it's your choices. And we never talked about it. And before this year, a lot of throwback. Steven, if you are listening to here, please come next Monday.
Got it.
Super. And you need it for the class for making evaluating reports of each other, and also there will be evaluation of instructor. So if you want school to fire me and write something bad about me, come on Monday and write it. So you already have the codes, most of you have the codes that work, propagate web packets for a specific system, and you can rerun it, and you have basic idea how to extract rates of reaction. So it appeals to your chemical soul. Some projects are not falling in this category, but this, whoever doesn't fall into this flow chart, I will address it personally. But more than half of the project fall into this category, into this flow chart. So you are selecting a model. In most of models, there is a barrier. So chemical reaction is like coming across the activation barrier. And then you select the model, you select the initial momentum which corresponds to the temperature. If you do not have this, the equation that converts your value of P naught into temperature, I would be happy to help, but it is like very simple. P naught square over 2 mass, and then multiply by conversion factor from atomic units to Kelvin. And then you run it and compute rate, like slope for population. And then repeat again with different initial momentum. And then you record this rate as a function of temperature, momentum as a table. Then we completely skipped it, but I will address it on Wednesday lecture and on the lab. So the table that you are generating is possible to fit into so-called Arrhenius law. Did you hear about it before? So I do not need to. And then out of Arrhenius law, one can extract activation energy. And your scientific question for those who fall into this flow chart is to compare height of a barrier and activation energy obtained through this indirect way. Typically, the activation energy from Arrhenius is lower than the barrier. And it is a key why many reactions happen at room temperature, although barriers are quite high. Okay, any questions? And this is printed on your reverse side. Make sense? And I just typed in steps how I would do it. If you have this stuff table, yield rate, and then from this table one can feed it into values. No. Do not read only upper right. Print 3 copies. It's not yet the end. So now the second part. I'm going to violate my own principles and do things that I think is very wrong. I was believing for many years that the instructor has right to tell only things that he or she memorizes with closed eyes and only show derivations. So showing pre-prepared slides is not fair. But to compress time, I will violate it and just jump a little bit quicker. It's not right because I should imagine myself on the other side and do one of the things that can be done in a short time. Starting the lecture. Who we are and what are we doing? It is a physical chemistry class. We do want to predict out or interpret outcome of the measurements coming for characterization of materials coming out of the instruments. And in order to explain and to make these predictions, we are getting through some counterintuitive wave properties of electron, interatomic distances, and rotations. And it's a little early to brag that in this room we are masters of space and time and universe, but there are some humble progress in some connections to experiments. There is one fundamental feature of any material molecule and substantial class of measurements that was not yet covered in the class. And there is a growing expert who will cover this subject in more details in the written report and presentation, and he is on the connection. So let's guess which popular characterization experiment we didn't cover in the class. Just make guesses. And if no one gives right suggestions, then Steven will put microphone on and answer, because I know that he has absolutely covered answer. Like we already covered spectroscopy, like UVs, partially infrared, partially rotational vibrational. We were speaking about ionization to some extent, about the electrochemistry of electrons being facilitated to leave or enter into multiple electron field. But what is in the second building of the Dunbar? What else? Yes. What is NMR? Okay. Electron spin will be EPR, but it is the same from math point of view. They are the same. EPR and NMR are several orders of magnitude different in signals, in frequency, space amplitude, but from mathematical point of view, they are absolutely the same. So, which property of the electron we didn't cover yet? Right. And it will be shame on me if we don't. So even in high school, when we all speak about hydrogen atom, we speak about 4 quantum numbers: principal, orbital, magnetic, and spin. Right? So it is kind of in our everyday knowledge background. So the goal of today's academic part of the lecture is to just make a step towards spin. And some classes in physical chemistry and quantum theory put it as chapter number 1, which is possible. And if we all would be mathematicians, it will be the shortest one. It doesn't appeal to intuitive nature of material scientists, but from a mathematical point of view, it's the simplest system. So there are several systems that can be described by pen and paper, like free space, box, oscillator, hydrogen atom, and spin. Because there are only 2 states. We are going to start covering what is it, and probably I'll squeeze a lot of material in today and Wednesday academic part of the lecture, so that you have some positive comments. What is this? Prediction. So through our effort in this class, you did a tremendous growth and progress towards advanced mathematical concepts, which may be a little bit too much for the physical chemistry course. But now you have your hands untied and can analyze complicated systems. So it's more like universal approach to quantum theory. And together we got some healthy benefits in understanding oscillatory nature of oscillators through creation and intuition operators. Instead of intuitive Cartesian projection, we were speaking in the space of abstract space of eigenstates. And then one can make this stickman who jumps between states. This is quite a universal approach. one is using the same approach for concept of spin, which is less intuitive. But mathematically, it will have a lot of similarities to harmonic oscillator. So mathematically, there will be raising and lowering operator, energy operator, number of excitations, which can be either 0 or 1. Cannot excite part of the system. So it is mathematical part of this thing. What was the last subject that we accomplished in this class? You know, huh? Yes, so like some basics of rotational motion. So if we approach spin not from mathematical point of view, but from the everyday common sense and scientific intuition, one should establish logical connection between rotations and rotational motion. So it is a extrapolation of the concept of rotations. I need to put microphone off and say something theoretical that will help you to go through the material, but please do not repeat it in public. If electron is like a little globe, then spin is rotation of this globe around itself, one direction or another direction. This is good for conceptual understanding, but it is wrong in many aspects. So if you select, instead of commerce, codings, chemistry, biochemistry, if you select physics major track, there will be problems like what should be the velocity of a surface of electron if it is a globe that rotates to get sufficient angular momentum. And the answer will be that it should be several times bigger than the speed of light. So it is not correct. It's only for us to understand. Now it's time to put microphone on again and introduce it a little more boring, not as bright, but more correct. So if by the end of the meeting we arrive to this slide again, it will be a good accomplishment. Too early to speak right now, but there will be briefly discrete vectors, space of vectors for quantum states, and matrices for derivatives. But since there are two states, all matrices are very small. From year to year, I am postponing typing in this equation, but it is maybe the most important equation of today's meeting if you are looking to a real life, to material science, to chemistry, to NMR or API. So if you have a system of spins, either electronic spins of electrons or spins of nuclei, then and you are setting up NMR facility, your observables will be related to magnetization of your sample. And magnetization, which is better, you will have a plate with compass or a plate of magnets, right? So it has direction. The magnetization depends on the orientation. So it is a vector. And spin, I'm introducing some concepts that I promise to support mathematics. Right now they are in the air. I invite you to accept them as hypothetical. So although spin has two states, but there is a way to speak about three projections of spin that can have orientation. Not just two, but three. And if orientation of spin in space is known, and we do have collection of many spins, then sample with all these spins generates magnetic field. And this magnetic field is proportional to summation of all spins together times a constant, which is called Bohr magnitude divided by alpha. So if you're looking into real life problems, you need this equation. From now on, I will stop speaking about real life and will speak only about spin vector, or what is needed for it. So charge of electron from constant mass of electron. So this whole fundamental concept. No, it's not an experimental matter. We will not get to this slide today. It will be likely last slide of Wednesday. And it will be dedicated, Wednesday will be dedicated meeting for Steven. So his project is related to NMR and will relate to the concept of spin vector with three components, performing motion or in circular way. And we will get simplest solutions, simplest example of such motion of a spin at the end of Wednesday meeting. Okay. It's 18 minutes before the end, and we finally start. So, oh, John is here. This was for you last time. I don't know if you were watching. So if you have circular motion, cross product, radius vector times momentum gives angular momentum, and mathematically cross product gives three components, x component, y, and z, right? And this will be projections of angular momentum. If it is two-dimensional rotation, it will be only z projection. And if we practice this determinant, then z projection will be operator of position for x dimension times operator of momentum in y dimension minus operator of momentum in x dimension times operator of position in y direction. Here is a space for 2 weeks of another lectures. If one carefully, remember, we were practicing position by momentum minus momentum by position commutation, right? And you all were successful. I remember. I saw you. If one practices the same approach, wasting like another few weeks on this projections of angular momentum, one will find another fundamental algebraic connections, commutational relations between these three projections. Before we had like only one dimension, position, momentum, and unity operator. Three operators were connecting to each other through commutation relation, algebra of operators. If we will have operators of angular momentum, they will also obey, if one plug in definitions and practices, these operators will obey so-called also commutation relation. So if one swaps, builds a product of rotation around x-axis and y-axis, and then swaps the dimension with the equivalent to the rotation around another axis. So there are commutation relations. They can be proved same way as we did for position moment, just a little more, but always waste of time. And it is a cyclic replaceable. If you put like x, y, and z, it will be correct. If you put x, y, and z, it will be also correct. So it's like a closed algebra. But how should we look on this? There are quantum operators corresponding to rotation around different axes. In a couple of slides, I'm going to give an argument that spin is analogous to rotation. And if we establish operators for spin projection in three directions, one expects that operators for spin projection should also obey similar commutation relations. Now you accomplished 2 weeks of rigorous. And this is a vector model of atom. Another. So, do not repeat in public that spin is the rotating wave. But if you have a sphere that can rotate, and angular momentum has different directions, but one sets up a restriction, same as all the time in the quantum world, that rotations are permitted only with a certain angular velocity, a certain value of angular momentum. And unlike massive objects, like rotation for titanium molecules, for rotations of spins, there are only 2 values of angular velocity permitted. One that corresponds to angular momentum constant over 2 rotation clockwise, and with negative rotating opposite counterclockwise. Right? Rotating one direction and another direction. This is not a new concept for you anymore because we already spoke about rotational motion like in Bohr models. For this magnetic quantum number, it can rotate forwards and backwards, right? Same for this spin. Rotates forwards and backwards, but not any integer number, but only one, like car with stick shift, only one transmission forward, one transmission backwards, and velocity can be either plus 5 miles per hour or minus 5 miles per hour. And it doesn't run immediately acceleration. So if you have 2 states of rotation, clockwise and counterclockwise, and do not forget never tell it in public, then this quantum system has 2 basis states: rotating forwards, rotating backwards. And one state is eigenstate, another eigenstate. But their superposition, when it simultaneously rotates forwards and backwards, which is a little crazy from common sense, but from the Bohr model consideration, you saw that one can build up superpositions of several rotations. Then, general state of spin will be superposition of these rotations forwards and backwards with generally unknown coefficients, if you didn't set up what is this rotation. If it rotates completely, for sure, clockwise, it will be c sub alpha 1, c sub beta 0. If it rotates opposite direction, this one will be 0, this one will be 1. If it will be like 50-50, it will be 1 square root of 1 square root. Good. So for model, this is the simplest implementation of Schrödinger. Nothing can be simple. A little quiz without grading, just inviting you to help. Feel the void. When we had regular rotations, angular momentum in units of Planck constant, absolute value was taken at 0, 1, 2, 3. Degeneracy was going like 1, 3, 5, 7. Like S, P, D, and then there are also values for dimensionless energy and CHEM. If we want to, I don't know how to explain it by word, but suppose we want to fill a gap, to have rotation a little slower than 1, and a little quicker than no rotation as well. What will be the value here, and what will be the degeneracy? Yes. Last year it was censored violence. Yes. So it's just summary what we just discussed. Energy of rotations with angular momentum Planck constant over 2 forwards or backwards should give the same energy. Maybe even, and it will be degenerous. Will be. Okay, approaching a little bit further to the tree. So, from mathematical point of view, there will be nothing new. You're already much more experienced than you were mathematically solving problems that are on the next level. So, in some sense, we are doing downshifting and living in the woods. If you have only 2 states, and one can speak about spin in the language of expansion coefficients over this distance, then no one forbids us to write down these expansion coefficients as a little column value. Right? No one objects. Then in this 2-dimensional space of vectors, the spin up will be expansion coefficients 1, 0, spin down will be 0, 1. And now we can write down this vector of 2 components as a superposition of 2 basis vectors with 2 projections. Same as we do in Cartesian 2-dimensional geometry, Euclidean geometry. 2 basis vectors, one is 1, and then any point in space is projections of x and y. Right? So alpha is 1, 0, beta is 0, 1. First 2 lines in equation. So now we are calling state man come to us. When we were speaking about density of states and harmonic oscillator, we called state man come to us. And it was transitions either in energy or just climbing different ladders. Right? Here it is a little oversimplified. There are only 2 stairs, two ladders, right? Or 1 step. Ground level and 1 step. But we can set up a procedure of walking up and down. Up with plus, down with minus. In such a way that applying this raising operator promotes us from alpha to beta, or an operator from beta to alpha. Make sense? Same logic. Now, can we, as you're already well familiar, any of you can just take the slides and present them. You're well familiar that if quantum state, if the wave function is a vector, then the operator is a matrix, right? Yes. So if the vector is 2-dimensional, the matrix should be 2-way. The question is, which matrix can we plug in place of this S plus and in place of this S minus? How can we find this matrix? We just write vector 1, 0, 0, 1 here and solve for unknown coefficients. Right? So it is not a tool to torture young minds. It's made by humans for humans to simplify life. And if you haven't solved we set up these equations that we need to solve for these 4 coefficients. But if you carefully do it algebraically, one would see that by practicing, if one fills 3 with zeros and 1 with 1, it will fill it. So if you do first for this element, you do row by column, right? 0 times 1, 0 times 0 will be 0. If you do second one, you get 1 times 1 plus 0 times 0 will be 1. Right? So it matches what we need. So it is algebra matrix representation of the whatever we call it. Whoever finds errors, please let me know for the spread and miss them once. I think you should call it class instead of class. Raising grade. Raising not like a dried grape, but more like green. Same way here. If you do row by column, you get 1 equal. So lower operator that promotes from B to 12. We are looking on the lines 2, 3, and 4 on the table, but we are not yet done. There is something on the right, and we need to cover it. Why did we admit Dirac notation? Brian, because it is universal. It allows to play some mathematical and algebraical tricks equivalently for continuous and for discrete representation. So, and by the definition of correct me if you see me wrong, but if we go raising from alpha to beta, it should be initial on the right, final on the left. If you go from beta to alpha, it will be initial on the right, final on the left. And one can check that such operator will transform beta to alpha, because there are like cat, bra, cat, but one can refocus on them and look these two betas as orthogonality relation. And then this cancels and will be alpha. Okay. And same with complementary operator. It also works for the same principle as we did to find the ground state of the harmonic oscillator. If you try to apply lower operator to the lowest state, it will give 0, right? Because of the beta and alpha through orthogonality are 0. So now we are completed line 3 and 4 of the dictionary, right? So the same operator can be represented either as matrix or algebraically through bra and cat. Last minute for overtime. You're overtime if you need to go for free. I'm not holding anything. It's completely thought. Very interesting observation. If you multiply these two operators by each other, notice that they both were off-diagonal. But if you multiply them, it will be diagonal. If you multiply them in the other order, it will be again diagonal, but the one will be in different place. If you add together this raising times lowering plus lowering times raising, it will give you a unit matrix. So same as in the A dagger A in harmonic oscillator, one needs to commute them to get 1. Here one needs to plus them to get 1. And if one, instead of coefficients 1 and 1, one puts energy of state alpha and state beta, it will be immediately Hamiltonian. The last slide. Okay, meeting is done. I'll stay here to answering questions.
heard what you said, where's the second one?